Hello, welcome to lecture 25 of the course. In the previous two lectures, we had a detailed discussion about the Cooper pair box and we have seen how a Cooper pair box can be realized as a two-level system. In this lecture, we are going to discuss about some other superconducting qubits, and this is going to be followed by our detailed discussion on the so-called Jaynes-Cummings model. So, let's begin. In the last class, we began with asking this question that what kind of radiation is needed to couple the ground and the excited state of a Cooper pair box, and taking the example of a Cooper pair box made up of aluminium metal. Aluminium behaves like a superconductor at the critical temperature of 1 Kelvin. We found that a microwave is required to couple the ground state and the excited state of the superconducting atom. And then we discussed about this circuit, how a Cooper pair is getting placed in a transmission line resonator, because a transmission line resonator can support a microwave, and putting a Cooper pair box in the microwave resonator, it can be coupled to the microwave signal. We also showed that indeed the transmission line supports a wave, and that wave is supported in terms of current signal or the voltage signal. We have discussed the so-called circuit model and found that the velocity of the voltage or the current signal is constant in the transmission line. We went on to discuss the quantization of LC oscillator via the canonical quantization procedure, and we found that the LC oscillator behaves like a harmonic oscillator when it is quantized, and we defined the annihilation and creation operator of this harmonic oscillator in terms of the magnetic flux operator and the charge operator. We went on to discuss the Hamiltonian of for transmission line, because the LC oscillator is the basic unit of a transmission line. It is obvious that the Hamiltonian is basically, for the transmission line, is nothing but a collection of harmonic oscillator. Each mode in the transmission line behave like a harmonic oscillator. Same is the case with the transmission line resonator also, which is formed by cutting a transmission line at two ends, and it supports standing wave, and this standing microwave also behaves like a harmonic oscillator. The signal that passes through a transmission line resonator is a voltage or a current signal. So if we consider a quantized transmission line resonator, then the voltage signal is also quantized, and we write a voltage operator. We express it in terms of voltage operator. We discussed then how this Cooper pair box is getting coupled to this voltage, and we found the interaction Hamiltonian, and this interaction Hamiltonian is given by this expression, but we need to focus ourselves on a two-level atom. So for that we need to keep our voltage or this parameter called Ng around 1/2, and then we'll be able to have this two-level system, as we have discussed this in great detail. Now, taking this excited state Kt and Kg as the basis state, this interaction Hamiltonian can be expressed in this particular form. And finally, we discussed how the field, the microwave field, the superconducting atom and its interaction can be captured through a Hamiltonian, and this model is known as the Jaynes-Cummings model, and we have written down the Hamiltonian for this atom and for the field and as well as the interaction, and this Hamiltonian is known as the Jaynes-Cummings Hamiltonian. Now let us extend our discussion on the superconducting qubit beyond the Cooper pair box. To this end, let us ask this question: is it possible to use a harmonic oscillator as a two-state quantum system or as a qubit? The answer to this question appears to be no, because we know that in the case of a harmonic oscillator, the energy levels in the harmonic oscillator, quantized harmonic oscillator, are equally spaced. So what happens is that if we throw a pulse to this harmonic oscillator, let's say this harmonic oscillator's consecutive energy level difference is h bar omega, then if this pulse has a energy h bar omega, then it can take an atom from the lower energy state to the higher energy state, and if the next pulse is getting incident, then it's going to take it to the another higher energy level, and this will continue. That's the reason it is not possible to confine ourselves to only two energy state, and therefore we cannot realize a harmonic oscillator as a two-state quantum system. However, if somehow we can break this harmonic ladder by appropriate engineering, let's say if we make the next energy level difference from, say, let's say this is the ground state energy and this is the excited state energy, and the next energy state, if we can make the gap larger than the energy gap between this first excited state and the ground state energy, that means, say we have this energy gap is h bar omega, and this energy gap is, say, E1, and if we can make somehow E1 greater than h bar omega, thereby breaking this harmonic ladder, okay, then it is possible to use this harmonic oscillator. In fact, it is no longer a linear harmonic oscillator, it's going to be an enharmonic harmonic oscillator. Enharmonic oscillator, I mean to say. Then we can use it as a two-state quantum system. And in fact, this is what is done in the so-called Josephson junction in the context of a superconducting circuit. A Josephson junction consists of two superconductors separated by an insulating barrier of appropriate thickness, say around 2 to 3 nanometer. This Josephson junction was discovered by Brian Josephson, and he got Physics Nobel Prize in 1973 for this discovery. Brian Josephson showed experimentally that because of tunneling of Cooper pairs, a supercurrent passes through the barrier, and this current is related to the phase difference between the phases of the two superconductors via a relationship, and this relationship is I is equal to I naught sine delta, where delta is the superconducting phase difference and I naught is the maximum current that can pass through the junction. Now we are going to understand this particular relation, which is very important for us, by using a simple quantum mechanical model. Say we have two superconducting electrodes separated from each other by a thin insulating layer like this, and this is our superconductor 1, this is superconductor 2, and across these two superconductors there is a voltage applied, say this voltage is V, and this setup can be expressed by using a set of coupled Schrodinger equation, and let me write this Schrodinger equation as follows: I h per del psi 1 del t is equal to E1 psi 1 plus k psi 2, and I h per delta psi 2 delta t is equal to E2 psi 2 plus k psi 1. Here psi 1 and psi 2 are the superconducting wave function for the superconductor 1 and 2 respectively, and you know that I can write psi 1 as a square root of rho 1, where rho 1 is the Cooper pair density, e to the power I theta 1 is the phase of the superconductor 1. Similarly, psi 2 is equal to square root of rho 2, where rho 2 is the Cooper pair density in the second superconductor, and theta 2 is the phase in the second superconductor. And here k is the coupling constant or the coupling parameter, and this coupling parameter is determined by the thickness of the tunneling barrier, that means the insulating layer, and the energy difference between these two superconductors E1 minus E2 is equal to charge of the Cooper pair, which is twice QE, into the voltage. QE is the charge of a single electron. Now one can easily get a set of equations for the time evolution of density and phase of the wave function in each electrode let me write these equations, and you can get these equations from this Couples-Schrodinger equation. I urge you to derive these relations that I'm now going to write, and it's very trivial to derive it. If you cannot do it, I am going to do that in the problem solving session. So the first one is rho 1 dot is equal to 2 by h bar k square into square root of rho 1 rho 2 sine delta, and rho 2 dot is equal to minus 2 by h bar into k square root of rho 1 rho 2 sine delta. And similarly for the time evolution of the phase in the first superconductor, that is theta 1 dot is equal to minus k by h bar square root of rho 2 by rho 1 cos delta minus QE V by h bar. And then for theta 2, that is the theta 2 dot, that's the time evolution of the phase in the second superconductor, that is minus k by h bar square root of rho 1 by rho 2 cos delta plus QE V divided by h bar. Okay, now here delta is equal to theta 2 minus theta 1, it is the superconducting phase difference. You can see from the first pair of these equations, that means from this set of equations, you can immediately see that rho 1 dot is equal to minus rho 2 dot. So this refers to the charge conservation. And the current across the junction is I is equal to rho 1 dot into some proportionality constant, say C0, and this can I now write as twice C0 if I put rho 1 dot, and rho 1 dot is equal to 2k divided by h bar square root of rho 1 rho 2 sine delta, and this I can now write as I naught sine delta here. So I is equal to sine delta, which was the equation got by Brian Josephson from experiment, and here we have got it using the model. And this I0 is defined as twice C0 k rho 1 rho 2 square root of rho 1 rho 2 divided by h bar. I naught is the maximum current that the junction can sustain. In other words, I naught is the critical current that can flow before the Cooper pairs break and superconductivity is lost. Now, from the other two pair of equations, one can actually show, assuming that rho 1 and rho 2 are approximately constant and equal, theta 2 dot minus theta 1 dot is equal to delta dot, and that is equal to 2QE divided by h bar into the voltage. And this I can also write as h bar delta dot is equal to 2QE into the voltage. Let's say this is our equation number 2. Physically speaking, in the presence of the potential difference V between the superconductors, the phase difference evolves in time, and we can write h bar delta dot is equal to h bar omega, and that is equal to 2QE into the voltage. Here omega is the angular frequency at which the supercurrent oscillates. Now recall from the previous class we defined the flux quantum phi 0. It was defined as 2 pi h bar divided by QE, and using this flux quantum we can write the time evolution of the superconducting phase difference as delta dot is equal to 2QE divided by h bar into voltage, and this I can now write as 2 pi divided by phi 0, the flux quantum, into the voltage. Say this is my equation number 3. Okay. Let me now show you using equation 1 and 3. Let me write the equations once again. Equation 1 was I is equal to I naught sine delta, and this equation I have delta dot is equal to 2 pi by phi 0 into voltage. Okay, using these two equation, let me say this set of equation is 4. Using this set of equations, taking the time derivative of this I is equal to I naught sine delta, I get I dot time derivative of the current is equal to delta dot I0 cos delta, and this I can write as I dot is equal to, instead of delta dot, if I put 2 pi by phi 0 flux quantum into voltage I0 cos delta. Now if I invoke the Faraday's law from elementary physics, we know that the voltage is equal to inductance into the time rate of change of current. This is the Faraday's law. Here L is the inductance of the Josephson junction, and if I put the value of the current, I get 2 pi by phi 0, the flux quantum, into voltage into I0 cos delta, and this is going to give me the value of the inductance, the magnitude of the inductance, as phi 0 divided by 2 pi I0 cos delta, right? As you can see, because of this cos delta term, the inductance is nonlinear in terms of this phase difference, superconducting phase delta. Now noting that delta dot is equal to 2 pi by phi 0 into the voltage V, and integrating both sides, say from minus infinity to time t, I can have delta dot dt dash is equal to 2 pi by phi 0, which is constant, into this integration minus infinity to t v of t dash dt dash. Alright, and from here I can now write, assuming that at time t is equal to minus infinity, the phase is equal to 0, superconducting phase difference is 0, I have simply delta of t here, and here I have 2 pi by phi 0, and this integration is nothing but the magnetic flux, because if you recall that this voltage is nothing but the rate of change of the magnetic flux. Okay, so this is an important expression. Here you see this superconducting phase difference is, we are now expressing it in terms of magnetic flux, and while we have done it, we have assumed that initially at time t is equal to minus infinity, that means initially the voltage is equal to 0, that means there is no potential difference between the two electrodes, and from here I can now write the expression for the inductance for the superconducting Josephson junction as phi 0, that is the magnetic flux quantum divided by 2 pi I0 cosine of this delta, which is your 2 pi divided by flux quantum phi 0 into magnetic flux phi. So this is the expression for the inductance of the Josephson junction. So you see the Josephson junction, which is formed by two superconductor placed adjacent to each other and separated by a thin insulating layer, can now be represented by a LC circuit, and this LC circuit we are having is a nonlinear LC circuit, because now the inductor is a nonlinear inductor. Now in the ideal case, when this inductor is a linear inductor, when quantized, this LC circuit behaves like a harmonic oscillator. That means the energy structure has the energy spacing between two consecutive energy levels are equal, spacings are equal. Now because of this nonlinearity in the inductor, this harmonic energy layer structure is basically getting broken. If we can choose the parameters judiciously, then this circuit, that means this Josephson junction, can be used as a two-level quantum system. This Josephson junction is symbolically denoted by this symbol X. In fact, it goes like this. So here you are having this current is passing through this junction, and the maximum current that passed through this junction is the critical current I0, and this junction is associated, Josephson junction has an intrinsic capacitance, and it is denoted by say Cj. Okay, and this is the symbol for the Josephson junction. However, more frequently the symbol that is used is of this type. You are having this box here, and with this double cross, this is the symbol for the Josephson junction, and the fact that it has a intrinsic capacitance Cj is also there, and this is what the symbol that is used most frequently for Josephson junction. Now, what about the energy stored in a Josephson junction? It's very easy to estimate, because you know that the power is given by current into voltage, right? So here P is the power, you know it from elementary physics, and power is nothing but the time rate of change of energy is called power. So therefore, if we integrate this power with respect to time, then say we integrate it from 0 to t, and I have I of t dash v of t dash dt dash. Then if I put the value of the current here, I of t dash is I0 sine delta dash, that's for the current, and for the potential we have, or the voltage, we have phi 0 divided by 2 pi, which is a constant, into delta dot dash here, dt dash, and because delta dot is nothing but d delta of dt, from this you can easily make it out that E is equal to I0 phi 0 divided by 2 pi, and integration is now going from 0 to superconducting phase difference delta, because delta dot is equal to d delta dt, and here you have sine delta dash d delta dash, and doing the integration you are going to get I0 phi 0 divided by 2 pi, and you have 1 minus cos delta, and this expression you can write it as the Josephson energy constant Ej. This is referred to as the Josephson energy constant. So in terms of it, you can write the total energy as E is equal to Ej into 1 minus cos delta. This delta can also be expressed in terms of the magnetic flux. So if I express it that way, then I have E is equal to Ej 1 minus cos of 2 pi divided by phi 0, the flux quantum, into the magnetic flux. So this is the expression for the energy for this Josephson junction. Let us now discuss about the so-called charge qubit. Okay, charge qubit we are now going to discuss. These charge qubits are a family of superconducting qubits which have a similar circuit design, and this circuit consists of a gate capacitor Cj connected to in series with the Josephson junction. So let me show you the circuit diagram. A typical circuit diagram for a charge qubit goes like this. You have a gate capacitance Cj, and then you have this Josephson junction. The symbol for the Josephson junction is what I am using here. So this is my JJ, that means the Josephson junction. And let me remind you once again that this Josephson junction is nothing but two superconductors separated from each other by a thin insulating layer. So this is what I have. Generally, the portion of the superconducting piece that is connected to this gate capacitance is called the island, while the other piece separated from the island by this thin insulating layer is called the reservoir. So here, uh, if I just write enlarge it, then the upper part is said to be island, and the lower part, which is separated from the island by this thin insulating layer, which is generally a bigger superconducting piece of material, and this is termed as reservoir. Okay. However, in the ideal case, this circuit can be shown by this diagram to have more clarity. The diagram goes like this. So we have this voltage, gate voltage, and we have this gate capacitance Cg. This is connected to this Josephson junction, and this Josephson junction has this intrinsic capacitance Cj, and by this cross we represent the Josephson junction, and this end, lower end of the Josephson junction, and the voltage is connected to ground. Cj and Cg, the gate capacitance and this Josephson capacitance Cj are in parallel, so the equivalent capacitance is C. This is denoted by this symbol C sum is equal to Cg plus Cj, because this capacitance Cg and Cj are in parallel. Then the charging energy can be written as HCH is equal to Q minus Qg whole square divided by twice of the capacitance C sum. You are pretty familiar with this form. The only difference is that earlier we wrote simply C instead of this more appropriate equivalent resistance C sum. Now, incorporating the Josephson energy, we can write down the total Hamiltonian for the charge qubit as H is equal to Q minus Qg whole square divided by twice C sum, plus the Josephson energy is Ej 1 minus cosine of 2 pi by flux quantum into the magnetic flux. Now here Qg is the gate charge, and that is equal to Cg into Vg. As Ej is just here, this particular term in the Josephson energy is a constant, and it's not going to contribute to the physics of the problem, and it's just an offset energy term. Discarding it, we can write down the Hamiltonian for the charge qubit as Q minus Qg whole square divided by twice of C sum minus Ej cosine of 2 pi by phi 0 into magnetic flux phi. Okay, again defining the Cooper pair number operators as n cap is equal to q cap divided by twice qe, and charge operator defining it as delta cap is equal to 2 pi by phi 0 into the magnetic flux operator phi cap, and defining the parameter Ng is equal to Qg divided by twice of Qe. We can write the general charge qubit Hamiltonian as H is equal to 4Ec into n cap minus Ng whole square minus Ej cosine of delta cap. Here Ec is the charging energy constant, and this is defined as Qe square divided by twice C sum. Okay, now this particular Hamiltonian should remind you about the Cooper pair box Hamiltonian that we have discussed in earlier classes. In fact, indeed the Cooper pair box Hamiltonian is an example of a charge qubit Hamiltonian, and different types of charge qubits are distinguished by this ratio EJ by EC. And in the case of Cooper pair box, we had EJ by EC is much less than 1. That means the charging energy part of the Cooper pair box, as you have discussed earlier, that the Josephson energy was very weak there. And in this case, if we have EJ divided by EC is much less than 1, then we get the so-called Cooper pair box, or the Cooper pair box out of this charge qubit. And Cooper pair box is a typical example of a charge qubit, as I have already said. In fact, it is possible to obtain the exact form of the Cooper pair box Hamiltonian that we have discussed earlier if we can write the Josephson energy in terms of the number state basis of the Cooper pair. For that, one need to use the Fourier transform pair for, say, this delta, the k delta, that is the state vector corresponding to the superconducting phase difference, and that is related to the number operator via this relation n is equal to minus infinity to plus infinity e to the power I n delta k n. Here this n is the capital N, and this number k n is related to k delta by 1 by 2 pi integration 0 to 2 pi d delta. I am taking an integration here because delta, the phase, is a continuous parameter, not discrete, unlike the number. Number of Cooper pairs are discrete, but the phase is not discrete. It can take continuous value from 0 to 2 pi, and here I have I n delta and k delta. I leave it for you as an exercise to get the exact Cooper pair box Hamiltonian using this Fourier transform pair. Otherwise, we'll try to do that in the problem solving session. Let us now discuss about another superconducting qubit called Transmon qubit. In such qubit, the Josephson energy is much greater than EC. This implies the Josephson energy, which is related to the magnetic flux, is much stronger than the charging energy term. Typically, in a transmon, this ratio of EJ and EC, EJ to EC, is on the order of 20. Actually, it lies between 20 to 80. Now consider this Hamiltonian. We are going to analyze it, this Hamiltonian, in the phase basis, that is delta, k delta basis. For small oscillation around the equilibrium point, the expectation value of the phase operator is 0, and we can expand the Josephson energy and truncate it to fourth order, expanding it around this equilibrium point. For that, we have to expand this cos term, cos delta term, and if we retain terms up to fourth order, then we can write the Hamiltonian in this particular form. And from this Hamiltonian, you see that the last term in the Hamiltonian is simply an enharmonic correction only. And in doing so, while we have written down this Hamiltonian, we have dropped the term Ng here, because this is going to have very minimal effect in the transmon regime. And similarly, we have dropped the energy offset term EJ, which we are going to get if we keep this term 1 in the Hamiltonian. That is going to give this term EJ, and that's a energy offset term only, and it's not going to alter the physics. As you can see that this Hamiltonian has the form of harmonic oscillator because it is quadratic in the number operator and quadratic in phase operator. And this, if we neglect this enharmonic correction, then this Hamiltonian is a harmonic Hamiltonian, harmonic oscillator Hamiltonian. And we can solve this Hamiltonian with this enharmonic correction term by considering this enharmonic term as a perturbation. To do that, however, first let us consider the harmonic part of the Hamiltonian. That means this Hamiltonian let us consider, and we have already seen how this Hamiltonian can be converted into the usual form of the harmonic oscillator Hamiltonian if we can define the phase operator delta and the number operator n. If we can write it in terms of this ladder operators B and B dagger, annihilation and creation operator, where we define this fluctuation, 0 point fluctuation term delta ZPF, which is the 0 point fluctuation associated with the superconducting phase difference, and NZPF is related to the fluctuation, 0 point fluctuation associated with the charge numbers. And if we define it in this form, then it can be shown that we can get a commutation relation between this phase operator and the number operator, and from there we can have this commutation relation between the annihilation and the creation operator. And in fact you can show it by trivial calculations. Please try to do this. Using these ladder operators, we can write the total Hamiltonian in this particular form. Very straightforward way you can get it, and written in this way, the transmons resemblance to the harmonic oscillator with a small enharmonic deviation is very clear. You see, this is the small enharmonic deviation in the Hamiltonian. Now the harmonic resonance frequency of the oscillator we can define as h per omega 0. Omega 0 is the harmonic the resonance frequency of the harmonic oscillator, and the prefactor of the nonlinear term is EC by 12, as you can see from this expression, and this term is small compared to h cross omega 0 for transmon. That means you have this condition, and from here you can get the ratio of EJ by EC, and that turns out to be around 9 into 10 to the power minus 4, and this clearly this means that EJ by EC, that ratio for a typical transmon is around 20 to 80, and therefore this relation that we have worked out clearly works here and it is valid there. Now we invoke the so-called rotating wave approximation, and if we invoke this rotating wave approximation, then we can expand the last term in the Hamiltonian, which involved is b plus b dagger to the power 4, and if we expand it, then we are going to get several terms. Okay, and these several terms, because of the fact that this annihilation operator evolves in time according to this expression where omega q is the oscillator frequency, and we have learned about this earlier, and if we put it in these various terms there, we will see that some of the terms are oscillating at frequency say 4 omega q, some are oscillating at 3 omega q, some are oscillating at twice omega q. That means many terms in the expansion, they are going to oscillate at very high frequency. Therefore we can discard this very highly oscillating term, and that is what is called invoking the rotating wave approximation. And if we neglect all the highly oscillating term, then the last term under rotating wave approximation can be written in this particular form, right? We are going to retain only these terms that we are going to get from the expansion, and the total Hamiltonian under rotating wave approximation can be then written in this final form. This particular form we can write it in this simple form, and this is the transmon Hamiltonian in the rotating wave approximation. Now defining h cross omega 0 minus EC as h cross omega q, where omega q is the oscillator frequency including the enharmonic term, and then we can write the final expression for the transmon Hamiltonian in this particular form. In order to get a quick idea about the difference between the Cooper pair box or charge qubit and transmon qubit, you can just look at their respective energy spectrum. That is what I plotted here. You see when EJ by EC is on the order of around 1, that is the domain of charge qubit, and as you can see from this plot that the energy levels are though there are separation is there between the ground state and the excited state. For example, if you just look at this domain, this one here, if you look at this portion, okay, you see there are energy levels are separated, but this energy are oscillating, and that is what is called decoherence. Now as you go on increasing the ratio EJ by EC, around EJ by EC around say 10 or 20 or say here 50, you see this oscillation in the energies are no longer there, and you are getting distinct energy levels, and therefore in the transmon regime the decoherence is reduced. However, enharmonicity is decreasing as we are increasing the ratio of EJ by EC. So therefore we have to be very careful in using transmon as a qubit, though it has this advantage that oscillation in the energies are very low, unlike the Cooper pair box Hamiltonian or the charge qubit. But in the transmon qubit, we get distinct energy level at the cost of decreasing enharmonicity. I hope you are getting the idea here what I mean by enharmonicity. You see, if you just look at this particular plot, last this subplot, you see there is a energy is given by difference in energy is square root of 8 EJ EC, and this energy level is also, it's almost equal to this one, but slight difference is there by this amount. Okay, so if you go on increasing it beyond 50, as you can see, then the enharmonicity is going to decrease further, and then you are going to get the usual harmonic oscillator as is can be seen from this particular plot. So we have to confine your parameters, you have to choose the parameters quite judiciously to get your transmon as a two-level atom. So if you use it as a two-level atom, then under this two-level approximation, the Hamiltonian for the transmon can be written as a two-level Hamiltonian, and there you have these two energy level. One is the ground state and another one is the excited state, and difference between these two energy level is h bar omega q. And then if this transmon is put in a microwave resonator, and this transmon is going to interact with the standing microwave present in the resonator, and then you can express the whole process by the usual JC Hamiltonian that we have discussed. And we are considering a single mode of radiation of the microwave. This is the part of the Hamiltonian describing the microwave which acts like a harmonic oscillator. This is the atom, that means the transmon, and this term represents the interaction between the transmon and the microwave. Now if we set our ground state energy to be 0 and the higher energy state as the excited state as s cross omega q, then this JC Hamiltonian can be written in the usual form like this, and this is what we have already discussed in the previous class. So this is the Hamiltonian we have. And by the way, just look at this last term in the Hamiltonian, s cross z sigma x a plus a dagger, where z is the coupling between the transmon and the microwave, and this sigma x can be written as sigma plus and sigma minus. Sigma plus refers to the atomic raising operator, sigma minus is the atomic lowering operator. And if I expand this term sigma x a plus a dagger, then I get several terms here. 4 terms we are going to get. Out of these 4 terms, however, if you look at the terms as sigma minus a, this refers to the physical effect that the atom is going from the excited state to the ground state. That is what means the atomic lowering operator, right? However, in the usual situation, what happens is that when an atom go to the ground state, a radiation is emitted. And here in this term, atom is going from the excited state to the ground state, but the radiation is absorbed. But in the usual situation, radiation is getting emitted or created. So therefore, the likelihood of this process described by this particular term is very little. Similarly, if you look at this particular term sigma plus and a dagger, This means that the atom is it's a raising operator, sigma plus atomic raising operator. That means the atom is going from the ground state to the excited state, and we know when it happens in the usual situation the radiation is getting absorbed, but here in this process radiation is getting generated or emitted, so therefore this process is also very unlikely to happen. That's the reason these two terms you can neglect or discard under the so-called rotating wave approximation. Then you can write this final Hamiltonian. This is called the Jaynes-Cummings Hamiltonian under the rotating wave approximation, and this Hamiltonian is exactly solvable. Let us make an attempt to analyze this JC Hamiltonian. Firstly, let us consider the case when the coupling between the atom and the field is 0. That means the parameter z is equal to 0. This means that the Hamiltonian, the JC Hamiltonian we have has only this field mode which act like a harmonic oscillator, and we have this atom, and the difference between the energy levels in this two level atom is h cross omega atom. That means we are having this situation, field mode is there, but it is not interacting with the atom, and atom has this ground state kg and excited state ke. We can define a parameter. This field mode has energy s cross omega, and difference between the energy level in the atom is s cross omega atom. It is not necessary that omega is equal to omega atom, so we are going to define a parameter called the detuning parameter, denoted by delta. This is called the detuning parameter, and when this parameter is 0, and we will say that we are considering a resonant situation. Okay, now in the combined basis of the field and the atom, if we consider the basis state of the atom kg and ke, and the field basis, if we consider it as a harmonic oscillator, so it is represented by this number state kn, then this combined basis state, we can draw the energy level scheme for this oscillator, for this system. So let us do that. So on the here we are going to draw in terms of energy. So we have, say the atom is in the ground state and there is no quanta in the field mode, then this is going to be the ground state for the system. Then we can put a quanta in the field mode, then we are going to get the excited energy state here, and this difference between the energy level is going to be h bar omega. Then if we put another quanta in the field mode, keeping the atom in the ground state, we are going to have this energy level, and this difference is also going to be h bar omega. So basically we are going to get a harmonic oscillator ladder. Or what we can have is that the atom is in the, say, excited state and there is no quanta in the field mode, then we are going to have the energy level Kate E0 here, and this is different from the ground state of the other harmonic ladder by h cross omega atom. And if we put a quanta in the field mode, then we are going to have this energy state keeping the atom in the excited state. So this is going to be the energy level, and this difference in the energy level is going to be, two energy level is going to be h cross omega. Then we can put another quanta in the field mode keeping the atom in the excited state, then this is the energy difference is going to be h bar omega. So basically we are going to have two harmonic ladders, and we are considering the coupling parameter to be 0. That means there is no interaction between the atom and the field. So what you see, that basically the difference between the adjacent energy levels of this harmonic ladder, two harmonic ladder, is h bar delta, because omega, we have defined the detuning parameter as omega atom minus omega. So adjacent energy levels in the harmonic ladder is different from one another by h bar delta. I hope all of you are getting it. We now aim to find the energy eigenstate when we switch on the coupling. That means when Z is non-zero, this coupling parameter, if it is non-zero, but this energy level structure here we are drawing it for when Z is equal to 0. However, what is the only difference is that now we are going to include the other term in the Hamiltonian. We had this Hamiltonian h cross omega a dagger a plus the atomic part h cross omega atom sigma z plus 1 by 2, and we have also now this interaction term. Now we are going to discuss the case when this coupling is non-zero. That means there is finite coupling between the atom and the field. Then we have to consider this full Hamiltonian, and we can draw similarly the energy level structure. However, taking a cue from the discussion that already we did for the level structure for the energy when the coupling is 0, we can take the basis state as we have this basis state Zn and En minus 1. If we consider this as our basis state, I hope you are getting the idea why I am taking it, because we are now going to focus only on the adjacent energy levels in the harmonic ladder, and from this adjacent energy level, you see these two adjacent energy levels are such that when the atom is in the ground state, there is a quanta say n in the field mode, and if the atom is in the excited state, the a quanta is getting absorbed from the field, so therefore there is a less quanta in the field mode. That's why it is n minus 1. So that's the reason we can take this as our basis state, and this is called the RWA, rotating wave approximation, because we will not bother about the higher energy states there, because the interaction may be more prominent between the adjacent energy levels in the harmonic ladder only, and the coupling between these two energy levels, adjacent energy levels, can be worked out very easily if we work out the matrix element arising from this interaction term, which is your S cross Z sigma x a plus a dagger, and we have the energy levels as say Z n and E n minus 1. So coupling between this energy state and this energy state is happening via this interaction, and here this sigma x, this is the Pauli operator, and this sigma x is related to the atomic raising and lowering operator as we have discussed. So sigma x is going to act on the atomic state, and a plus a dagger is going to act on the number state of the harmonic oscillator. And it's very trivial to show that if you do the calculation, you are going to get h cross z square root of n. What it means? This means that you are going to have this kind of a energy level diagram, and this is the coupling scheme under the rotating wave approximation. So you see, this is the matrix element you are getting out of your calculation, and please try to do this result, otherwise we are going to show it in the problem solving session. Now the adjacent energy level, you see these are connected. For example, this energy state and this energy state, the coupling between them is energy is S cross Z. Similarly, if you go to the higher one, then coupling is S cross Z square root 2 and so on. We can write down the rotating wave Jaynes Cummings Hamiltonian in the matrix form. To do that, we consider the basis state as this, the atom in the ground state and n number of quanta in the field mode, and another basis state corresponds to the atom in the excited state, and there is one less quanta in the field mode. So this Hamiltonian, Jaynes Cummings Hamiltonian in the rotating wave approximation can be written in this form, which we have written already. Now taking Kate alpha as Kate Gn and Kate B beta as this, just the shorthand notation for this particular basis state. Using this shorthand notation for the basis states, I can write down the JC Hamiltonian in this particular form, and we are familiar with this particular form, right? Because the basis states are here, Kate alpha, Kate beta. So we are going to have in total 4 matrix elements for the Hamiltonian, and we have to calculate all of them. And let me show you a typical calculation here. So say H alpha alpha is this matrix element. First let us find out what is H alpha, and alpha is K zeta n, right? So if this Hamiltonian, let me explain you term by term. First of all, this field mode part of the Hamiltonian is acting on the this basis state Gn. Now because this field mode is a harmonic oscillator, it's going to act on the Kate n only, because that corresponds to a harmonic oscillator, that's the field mode. And because A dagger A is the number operator, so you are going to get this expression. Now coming to the second term, which is the atomic term. Now here the atom is in the ground state if you look at the basis state, and when the atom is in the ground state, sigma z is, you can take it to be equal to -1 for atom in the ground state. You can take it to be -1, then you will see this term is going to vanish, so therefore you will get 0 for when it is going to operate on the basis state, you are going to get 0. And in the next term you see sigma plus, which is the atomic raising operator. When this sigma is going to operate on the ground state, it is going to take the atom to the excited state. And when sigma plus and sigma minus, on the other hand, atomic lowering operator, when it operates on the ground state of the atom, it is going to give you 0, because there is no any energy level below the ground state. So applying this, and similarly A when operates on the Kate state n, then it's going to give you root n n minus 1, and because of this reason you are going to get this term from this last term. Okay, I hope you get it. Then therefore H alpha, after you get this H alpha, then you can take the scalar product with Kate beta bra alpha, and immediately you will see that this state and this state is normalized, and because of that you are going to get H bar omega n, and this particular state and this state are orthogonal to each other, so that is going to vanish. So you will get H alpha alpha, this matrix element, to be H cross omega H bar omega n. Again H beta you can calculate in the similar way. Now this time the atom is in the excited state, so from this middle term here you have to put sigma z is equal to +1, and this is going to give you this particular term. And similarly, as I have explained, you can make it out that the field mode when is operating on the basis state here is going to give you this term, and the last term is going to yield this particular term. Therefore you are going to get H beta beta as well, and H beta beta is going to give you this matrix element would be H cross omega n plus S cross omega atom minus omega, and S cross omega atom minus omega is nothing but the detuning parameter. So H beta beta, this matrix element, you are going to have H cross omega n plus H bar or S cross delta. Similarly, you can find out the other two matrix element of the Hamiltonian, H alpha beta and H beta alpha. That's going to be H cross z square root of n, H cross z square root of n. So thereby we are having all the terms in the Hamiltonian, matrix elements in the Hamiltonian, and JC Hamiltonian therefore can be written under the RWA, it can be written in this form. Now you can easily see that at resonance, that means when detuning parameter is equal to 0, that is delta is equal to 0, or field mode frequency is equal to the atomic frequency, the Hamiltonian is going to look like this. Here now delta term is no longer here. Okay, this term is 0, delta is equal to 0, and it is easy to find the energy eigenvalues, and energy eigenvalues are going to be E plus is going to be given by h cross omega n plus h bar z square root n, E minus is h bar omega n minus h bar z n. And what you see, because of the coupling, because here z is non-zero, because of the coupling, the degeneracy in the energy level is getting lifted, and also you can find out the energy eigenstate corresponding to this energy eigenvalue E plus and E minus, and the energy level E plus, which is going to correspond to this K T plus, is going to be simply the symmetric superposition of Zn and En minus 1, and another energy state E minus is going to be antisymmetric superposition of Zn and En minus 1, and this can help you to get the energy level structure for the atom, this field atom system, and you see you are going to get this energy level structure. And as I said, because of the fact that this coupling is non-zero, because of this non-zero coupling, the energy level are no longer degenerate. That means because of the coupling, the degeneracy is getting lifted. For example, if you look at this energy level Z1 and E0, which are degenerate when there is no coupling, that means Z is equal to 0, but because of the coupling, these energy levels are getting non-degenerate, and the energy difference between them is twice h bar z. Similar is the case with this energy level kz2 and kte1, which is degenerate when the coupling is 0, that means z is equal to 0, and because of the presence of the coupling, now they are getting non-degenerate. The energy difference between them is 2 root 2 h bar z. Now what about the dynamics of the system? If we ask this question, if we have the atom in the ground state and n number of photons in the field mode, what happens in time? Well, at time t is equal to 0, we can write the state vector for the field and atom system as k psi 0 is equal to Gn, that means the atom in the ground state and n quanta in the field mode. Then at time t, the state vector for the system can be written as a superposition of the eigenstate of the atom field system, which we have already worked out, ket E plus and ket E minus, and their corresponding energies are E plus and E minus. By the way, we are considering here the case delta is equal to 0, that means the resonant condition, and we have worked out E plus, and that is the symmetric superposition of ket Gn and ket En minus 1, and similarly E minus is the antisymmetric superposition of ket Z n and ket En minus 1. Then these are the coefficients C plus and C minus. Now at time t is equal to 0, this particular state ket psi t should give us ket Zn, and you can revive this expression ket Zn from this one, from this expression here. If you take C plus and C minus to be equal to 1 by root 2, okay, and you can easily verify that. Therefore we can write down the state vector at time t by this expression here, and in order to find the ground state probability for the atom to be in the, that means to find the atom in the ground state at a later time t, you have to calculate this particular quantity. You want to go from the state psi of t to the state Gn, and if you make the calculation, you are going to get this expression for this probability, ground state probability, and this is what you are going to get. It should remind you about the ground state probability that you have got for the case of the classical field, when we have considered the field as a classical field and the atom as quantized. In the semi-classical case also we discussed, and this gives rise to the so-called Rabi oscillation. As you can see from this plot, the atom is going to oscillate between the ground state and the excited state. If we compare the semi-classical expression for the Rabi oscillation, where we have calculated the ground state probability with that of the quantum case, you can easily see that this quantity 2g root n, root over n, plays the role of Rabi frequency. In fact, if we go on increasing the number of quanta, n if much greater than 1, then this quantum case is going to approach the classical case, and if we increase the number of quanta in the field mode, the Rabi oscillation is also going to increase, as I am now showing it in this plot. Now we can go on discussing the case of non-resonant case as well, where this detuning parameter is no longer 0, delta is non-zero. However, the most interesting case is the case of dispersive regime, and which is of great relevance for superconducting qubits. And in this dispersive regime, the detuning parameter is much greater than that of the coupling parameter. This we are going to discuss in the problem solving session. Let me stop here for today. This lecture concludes our discussion on circuit quantum electrodynamics. However, in the next lecture, which is going to be a problem solving session, we are going to solve some problem based on whatever we have learned in the last 3 lectures, including this one. So see you in the next lecture. Thank you so much.